So this is the Geeks for Geeks problem of the day, June 2nd, 2025. Unique paths in a grid, difficulty medium. You are given a list, a 2D list, a matrix, so to speak, called grid of size n by m, consisting of values 0 and 1. Value of 0 means you can enter that cell. Value of 1 implies that entry to that cell is not allowed. You start at the upper left corner of the grid, 1, 1. We're actually going to call that 0, 0. And you have to reach the bottom right corner, n, m, and we're actually going to call that n minus 1, m minus 1. You can only move to the right or down from every cell. And your task is to calculate the total number of ways of reaching the target. Note the first, the cell in the upper left corner and the cell in the bottom right corner can also be 1, which I take to mean that you can't get in there. So if either of those is 1, then there will be no paths in the grid. Guaranteed that the total number of ways will fit into a 32-bit integer. All right, that's good because the code that this is the method signature that we were given, and that is unique paths, and the return type is an int. All right, let's see. Constraints. We can have up to 1,000,000 cells. Expected complexities, time complexity is O of n times m, which means we're going to have to visit each cell one time. Auxiliary space is also O of n times m. That would be typical of a dynamic programming solution. Company tags, Uber apparently likes this question. This is not an uncommon question. I mean, maybe the twist on it is just that there are obstacles. I mean, it's a pretty standard problem. You know, here's a grid, and how many paths are there from the upper left corner to the bottom right corner? You could do it with combinatorics. With a big grid, that might be more efficient. I don't know. You would wind up doing it with a binomial coefficient, but it's we're going to do dynamic processing. You can also do it with recursion. If you do it with recursion, you're going to have a lot of repeating subproblems. And so, you know, with 1,000,000 cells, you are not going to be able to pass something like this within a reasonable time limit. I tried that, by the way, you know, just to verify it. I typed in a recursive solution, and it does, in fact, time out. So we'll go with dynamic programming, topic tags. Yeah, dynamic programming, and the other three are pretty obvious. So let's see. There's a couple ways of doing dynamic programming. There's top down and bottom up. Top down is called memoization. Bottom up is called tabulation. Memoization is like a recursive implementation. But the difference being that you store the results of function calls in a table, so you can just look them up. So you'll have the repeating subproblems, but you won't compute them every time because you stored them in a table. Okay? Tabulation, which I think works well with this. You know, we're dealing with really a table anyway. It's called a bottom-up approach, and it stores the result of subproblems in a table. It's an iterative implementation. You might say, well, why is it bottom up? Aren't we going from the top of the table to the bottom? And I mean, directionally, yes, but it's bottom up because the entries are filled in starting with the smallest and building up to the final size. So let's take a look at what we might do with this. Where is my cursor? Okay, here we go. So we get a grid in here, and we want to save the length and width of the grid in variables. We'll call those M and N. Here is our auxiliary space, a dynamic programming table. We'll call it DP. Sometimes people call it memo. I mean, you can call it anything really, but DP and memo, actually memo is not, if I think about it, memo is not as good for this. Let's call it DP. All right. First thing we're going to do is we're going to take into account that the first cell, the top left cell, could be a 1. They told us it could be a 1. So if it is, if grid 0, 0 is a 1, we're done. We can't even enter that cell. So we'll just return 0. There's no paths. Okay? If that is not the case, then we initialize DP 0, 0, the dynamic programming table, to 1. How many paths are there to that first corner cell? And there's 1. All right, now we're going to do a nested loop through the rest of the cells. And we can only move right or down. Okay? So we've got a nested loop here. We're going to go through the cells of the grid. If the grid, if the grid cell that we're currently considering is 1, that's an obstacle, and that means we can't get there. So in the dynamic programming table, what we're going to do is we're going to put a 0 in there, meaning there is no path by which we can get to this cell, and then we'll just go to the next cell, hence the continue statement. All right, if I is greater than 0, what does that mean? It means that we are not in the first row, okay? If we're in the first row, there is no cell above the current cell. But if I is greater than 0, there is a cell above the current cell, and we want to add the number of paths to that cell to the current cell. So dpij equals dpi minus 1. That's the cell above the current cell. We'll add that value to the current cell. If j is greater than 0, what does that mean? That means we are not in the far left column. If we are in the far left column, then there's no cell to the to the left of that cell. So if we're not in the far left column, then we want to add the value, from the cell to the left of the current cell, because again, we can only move down and to the right. So we'll take the value from the cell to the left of the current cell, add it to the current cell. And when we get to the bottom right corner, we'll return the final answer. Now, it is possible that the bottom right cell is a 1, meaning we can't get in that cell, but we handled that here. If the grid ij, when we consider the bottom right cell, which would be the last cell that we look at, if it's a 1, then we put a 0. in the dynamic programming table. So this will be 0. Okay, actually, it just occurred to me that maybe an example of this would be helpful. We'll use this example here, the first one, where the grid is as shown, and the DP table. I'm going to ask you, so I don't have to like write and erase so many things, to just envision that it starts out, if we do something like this, declare an integer, a two-dimensional integer array of, a two-dimensional integer array. Java is going to initialize that to zeros. So imagine that we have a 3x3 array of zeros. Okay. So the first thing that we do, since grid 0, 0 is not 1, is we put dp 0, 0, we set dp 0, 0 to 1. Okay, and now we're in the loop here. If I 0, 0, okay, so we look at I 0, 0. We don't do anything with this because we have if I is greater than 0, which it isn't, if j is greater than 0, which it isn't. There's nothing else we can do with this one, so we're going to move to the next the next cell. All right, so that cell is 0, 1. Is I greater than 0? No, there's nothing above that. So we just take the cell to the left and add it to that cell in the DP array, and then we go to the next cell, and the same thing is going to happen. There's no cell above it, but we can add the cell to the left to that array. All right, now we're going to go down here. Now we are at 1, 0. Okay, there's nothing to the left of this cell, but there is something above it, so we'll come down here and we will add 1 to that. We go to the next cell. Now we've got an obstacle. Okay, so now we hit this grid ij equals 1. So we set this to 0, meaning there's no way to get to that cell. Okay, move to the next cell, and we have a cell above and we have a cell to the left, and we add them together and we get 1. There is one unique path to that cell. All right. Last row, 0. There is nothing to the left. We add the cell on top and we get that. Next cell, we add the cell on the left and we add the cell on top together, and that is 1. And then finally, the last cell, we add the cell on the left, we add the cell on top, and we get 2. And is that the right answer? Where's it? Oh, here it is. Output 2. Okay. So, well, it works on paper. So, I mean, let's try running it. The submit button is actually out of the frame, but I want to be able to see the results in the frame, so I'm going to do it this way. Okay. Attempts, correct, total. Oh. I think it's like counting some of my previous attempts where I tried to do like recursive solutions that don't work. Okay, good. So that is the problem. That is the problem of the day. Please go ahead and like, subscribe. If you subscribe, you'll get notified whenever there is new content. I'm going to try to do these. I'm going to try to do the problem of the day every day, or at least on weekdays. So, yeah, that's it. I'll see you next time.